All right, so now let's do a buffer problem. So our buffered solution contains acetic acid and sodium acetate. So we've got our acid and its conjugate base. So this right here, this is just a common ion problem like we did before. Now, I'm going to use the generic HA for the HC2H3O2 just so that I get to write less. You know I'm always a big fan of that. All right, so there's our reaction. We've got 0.5 of the acid, 0.5 of the common ion, 0 of the H plus to begin with. Got our minus X, plus X, and plus X. So we have 0.5 minus X, X, and 0.5 plus X. Okay. Our Ka, H plus, A minus, over HA. So we have our 1.8 times 10 to the minus 5 equals X times 0.5 plus X over 0.5 minus X. Okay. Our approximation lets us drop these, which would give us 1.8 times 10 to the minus 5 equaling X, which is equal to our H plus. But let's play it safe and use our numeric solver. So we go here and we have 1.8. Whoa, okay. Times 10 to the minus 5. And we have 0.5 minus X. And then on the other side, we have X times 0.5 plus X. Okay. And so we hit OK to solve. We've got our answer from the last time we did it, so we hit solve again. And we have 1.799 times 10 to the minus 5, which confirms that, yes, that is what we have. So we want the pH of that, so we need our calculator again. Get to my regular screen. Negative log 1.8 times 10 to the minus 5, and I have that our pH is 4.74. Okay, now the whole thing about a buffer is remember a buffer resists pH change when you add acid or base. Okay, so our buffer should maintain a pH of very close to 4.74, but we've got to check that. So let's look at this. If we have, let's find it. Here we go. All right. If we add 0.1 mole of solid NaOH to 1 liter of water, okay? So this is water. So this is not our buffer. This is just, what's the pH of 0.01 moles per 1 liter, so 0.01 molar sodium hydroxide, which is a strong base. So the OH concentration is equal to the whole concentration of the base, because strong base means completely ionizes or dissociates. So the OH is negative log of the hydroxide ion, and our hydroxide ion here is 1 times 10 to the minus 2. So my pOH is 2.00. pH plus pOH is 14. So my pH is 12. Okay, so if we add that many moles of sodium hydroxide to water, we're going to have a pH of 12. But what if we add it to our buffered solution? Okay, so all right, so we've got to do some stoichiometry. We've got to mark in moles. Don't worry, it's a lot easier than the stoichiometry that we had before. All right, so we've got our acid, and it's reacting with the OH minus. Because remember, we said that if you add a base, the acid would neutralize it. If you added an acid, that conjugate base would neutralize it. Okay, so that's going to give us our A minus and water. Okay, so remember, we need to work in moles here. So fortunately for this problem, I gave you 1 liter. There we go, 1 liter. So our moles and our molarity numerically are the same thing. So we have 0.5 moles of this, 0.01 mole of this, none of this. And I'm doing this stoichiometry very much like a rice table. Now, this is going to react. And if the HA reacts with that hydroxide, oops, I made a mistake here. That is not starting at 0 because we're a buffer system. So it's starting at 0.5. Okay. So when 0.01 of the acid reacts with the hydroxide, we are left with 0.49 moles. All of the OH goes away. And now we have 0.51 moles of that. So in 1 liter, so moles and molarity are the same. So now these are the new initial concentrations for another rice table. Okay. So I'm almost running out of room here. All right, so do our HA, H plus, plus A minus. Our HA initially is now 0.49. Our H is 0. 0.51 for our A minus. We still have a minus x. We still have a plus x. We still have a plus x. So we have 0.49 minus x. We have x. We have 0.51 plus x. So same Ka. Go back up here to this one that we did originally. We've got the same Ka set up. We've got the same Ka value. So 1.8 times 10 to the minus 5 is equal to x times 0.51 plus x over 0.49 minus x. Okay, now remember our approximation, our plus x and minus x, we can end up dropping, but our numeric solver does it for us. Don't need that second function. So let's see if I can, there we go. Okay, so in here, I need to change that one to 0.49 minus x. And down here, 0.5, okay, 1 plus x. And hit OK. It's got my answer from last time. Do it again. And I get 1.729. 1.729. So I get 1.729 times 10 to the minus 5, rounding to significant digits, 1.7. Look what we had before, 1.8. So our H plus concentration didn't change much. Therefore, guess what? Our pH .77. Did not change much. Okay, so now let's look at if we did the approximation. Okay, so if we drop the plus x and the minus x, we get 1.8 times 10 to the minus 5 equals x times 0.51 divided by 0.49. So 1.8 times 10 to the minus 5 times 0.49 divided by 0.51. And there we go. And our approximation by dropping the x matches what we get with our solver.